Welcome back friends. So today uh, last week we have been looking at in the last lecture we have been looking at various currents which the Dirac theory can write it essentially, and from that we have seen that there are these 5 different kinds of currents one can write down: the scalar, the pseudo scalar, the vector, axial vector, and so on. So essentially, and now each of these currents are important and they have some physical implications, very strong implications as for various cases. For example, the scalar theories are essentially Yukawa interactions. The pseudoscalar theories are theories like axions, kaons, pions, and so on. So, okay, the pseudoscalar theories, of course, there are scalar mesons essentially. So, if you have a pseudoscalar theory, it couples to the coupling of pions and scalars to nucleon current sometimes could be a pseudoscalar current essentially. Then there are vector currents and then there are axial vector currents. So, which are very important, the combination of these two which lead you to weak interactions. Then we also talked about tensor currents which we can write down for the Dirac theory, which is with the sigma mu nu operator, psi bar psi sigma mu nu operator. Okay, the axial vector current contains sigma psi bar gamma phi gamma mu psi, and the vector is nothing but this thing. Now I left it as an exercise to show under Lorentz transformations how these currents are classified exactly as how they transform under Lorentz transformation, and I left it as an exercise to show that you have to show that this transforms exactly, the scalar current exactly transforms like a Lorentz scalar, and the pseudo scalar transforms like a pseudoscalar, and I showed you the transformation property. It picks up the sign of the delta lambda, the Lorentz transformation matrix. And then we also talked about vector and axial vector currents. They exactly transform like vectors under Lorentz theory and axial vectors under Lorentz theory. The tensors also transform like tensors with the 2 indices. Okay. So, these classification of various currents and of Dirac wave functions is in terms of their Lorentz transformation properties essentially. So, this is so the entire course, as I have been saying, essentially crucially depends upon Lorentz system, because we are talking about quantum mechanics in the relativistic regime. Now, if we go further, we talked about examples, we talked about Yukawa interactions, okay, and then for the first time I introduced something for you. So, we introduced Yukawa interactions, so in which there is an electron going in and then coming out essentially in terms of time, and it exchanges a scalar particle, and this and is absorbed by another electron essentially. Now, all these things will become a bit clearer. The phi here, the dotted line, is something called a propagator, and the electron a wave function is written in this particular fashion, that is an incoming electron, and the dot, the big dot here is essentially something called a vertex, that tells you what is the interaction picture. This is exactly what we want to do in a calculation in a relativistic regime essentially. Now, this entire framework which I introduced you essentially is in the context of completely relativistic theories which are like quantum field theories. They are not this is a framework of quantum field theory. Now, why I am coming to quantum field theory framework? Because I have written the Lagrangian in completely, the moment I write a Lagrangian, it shows that it is a completely relativistic theory, and so I have to introduce these particular aspects essentially. Now, if we are doing relativistic quantum mechanics, the feature is different, because we want to introduce wave functions, we want to introduce potentials essentially compared to introducing mediators, essentially force carriers or something. Force carriers are invariant in a relativistic regime. Okay. Now then we talked about the so suppose if I do not want to do this completely relativistic calculation, I want to do like relativistic quantum mechanics, and we have seen that there are problems associated with antiparticles and which are create problems which are like Klein paradox and Zetter-Bitter-Wiegang. Do they also exist in Dirac theory, because Dirac theory also has negative energy solution? And the answer is a resounding yes, and these problems do exist also in Dirac theory essentially. Now there is also okay now but so these consider the example as a simple example of Klein paradox in the Dirac case. Essentially we are not explicitly doing that, but we argued that this will be exactly the same calculation what we did for the KG case, except that the wave functions are now u and v. So suppose if I just start with the Dirac equation with a potential V of r. So like here, so I started with the Dirac equation like here, okay. I started with a Dirac equation with a particle, but now my wave function is multiplying a potential. So I am doing relativistic quantum mechanics. Now the problem incidentally here is that this x and this x are different, because this x is only a space time x and this x is a completely x mu essentially, because in principle you can write okay this x what we have done is this del slash is a theory of for completely 4 dimensions, space time and 4 dimensions, but you just start you write a potential Hamiltonian, Dirac Hamiltonian, the Dirac equation just by introducing a wave function in this particular fashion essentially. Now if you do this, then the problems will be exactly the same as what happens in Klein-Gordon equation. So you can imagine that I throw away all the negative energy solutions, I take only a positive energy solution and introduce a barrier with a height of V0, and then the wave function comes in from the left exactly like in the case essentially, and there is a reflection coefficient and the transmission coefficient which you can compute in the 2 regions of the potential. So we can call this as region 1 and this as region 2, and then we introduce continuity and continuity of the derivative and the continuity of the wave function across the boundary. Now when we do this calculation, and we have seen we had done this calculation again in the case of KG, exactly the same case. If it is a weak potential, you have sensible results. The potential is extremely weak, meaning the height of the potential is much smaller than the electron mass. Say for example here we are considering mass of the particle to be electron. We can consider several other cases also, but the particle the mass of the height of the potential is smaller than the rest mass of the 2 times smaller than the rest mass of the particle, then you get sensible results. The moment you have a strong potential, meaning in the sense that V0 is much larger than 2 MEC square, then you get nonsensical results. Again you end up having a Klein paradox. R plus T will not be equivalent to 1, R will become negative, T will become imaginary, and those kind of situations you end up having essentially. So same thing with Zetter-Bitter-Wiegang, we saw that the currents will be rapidly oscillating with because of the presence of the negative energy solutions essentially. Both these things will be repeated in the case of the Dirac equation. Okay. So the paradoxes continue with the Dirac equation. So the calculation of a completely non-relativistic potential in the Dirac theory will lead to nonsensical results in the limit of strong potential, exactly like in the case of Klein-Gordon equation. Now there is something which is interesting, which we call as the Dirac theory, Dirac hole theory. Now Dirac realized this, and then what he said was that so Dirac realized this, and then Dirac equation does not solve the negative energy solutions, negative energy solutions problem essentially. Okay, solutions. So Dirac proposed a radical solution for the case of electrons essentially, because electrons satisfy something called the Pauli exclusion principle, because they have spin. You cannot put two electrons in the same state essentially. So what he said was, okay, what he said was, because now suppose if there are negative energy states which are systematic, and now suppose paradox with Dirac. So one of the main paradoxes with Dirac negative energy states is, because now they are talking about this, talking about electrons. Now you have a nucleus, and suppose imagine that there is a electron revolving around a atom essentially. Okay, so there is a nucleus which is like a hydrogen atom. Let us imagine that there is a proton and a neutron, hydrogen, or okay, let us just take simple atom, and electron is moving. Now there are states which are not only positive states essentially like this, but below 0 there are also negative energy states essentially. So in principle the electron which is sitting here, say for example if it is sitting here, now can continuously start radiating photons, can continuously start radiating photons, can shift to lower and lower, lower and lower, lower and lower, completely negative infinity, negative energy infinite state essentially in principle. So it can keep giving out several photons, okay, it can keep giving out several photons, and the electron can completely go down to the negative energy state, and the atom should collapse. Now this is what, if you are thinking in terms of quantum mechanical systems essentially, if you have thinking relativistic systems in a quantum mechanical setting essentially. So we will come back to this hydrogen atom again, but for the present I will just describing this thing. Now this is a paradox essentially, but this is not happening. Atoms are not collapsing, and atoms are stable and everything. This goes against the complete Bohr picture and everything. To solve this problem, what Dirac said was that all the negative energy states are completely filled up of the electron, or completely filled up, exactly like what I showed you in the previous slide essentially. So he said that all the negative energy states are completely filled up in nature, okay, they are filled up, and so nothing can go and fit it in another in the theory essentially. So no other electron can go and sit in that space essentially, because the entire energy states are completely filled up. And what we observe in nature are nothing but energy differences with respect to vacuum. This is a very crucial step essentially. The Dirac C is a very crucial step, because in some sense it is a precursor for the quantum field theory essentially. It sets the ground for the quantum field theory, and in many ways it is equivalent to quantum field theory picture, but though exactly not essentially. So there are some formal differences, but in some cases, but it does not really matter for as long as we are considered with linear operators, this is almost exactly the same case as quantum field theory picture essentially. So, the Dirac theory is exactly like in a quantum field theory picture. So, that is the reason why the Dirac hole theory is a very important thing. Now, suppose if you fill up all the states like this. So, if in an electron essentially, so what we are measuring is the energy differences are only the differences between these two states. Say for example, the photon energy here is a difference between this state and this state. Say for example, let me call this as E2 state and this as E1 state. Delta E2 E1 is equal to E2 minus E1, but the E2 state would have the full vacuum energy essentially. So, E2 state would be E2 plus E vacuum, E2 0, say for example 0 to 2, and then full vacuum energy, which is nothing but the entire negative energy states energy minus E10 minus E vacuum. So, the vacuum thing completely cancels off. So, you understand that the vacuum is just like a constant which is being added, and above which what we are seeing is the differences. This is only the measurable quantity. So, this is only the measurable quantity, the gamma is only the measurable quantity. The energy of the gamma, which is the spectrum of the photon essentially, which is being emitted as the electron moves from the state E2 to E1, and E1 state has an energy which is the energy of the vacuum plus from the energy from 0 to 1, say for example, okay, 1 0, and energy of the E2 state is nothing but the energy of the vacuum plus energy from 0 to 2, okay, 0 to 2. So, that is E2 0. So, this is nothing but E2 minus E1. So, the vacuum energy completely is vanished because we are only worried about the differences. So, Dirac made this radical hypothesis that the entire vacuum states are completely filled, okay, completely filled, which is called as the Dirac sea. So, this entire thing is called the Dirac sea. Now, there is no other electron which can go in, because of the Pauli exclusion principle, because Pauli exclusion principle tells that electrons, no two quantum numbers should be the same for a particle occupying a state essentially. So, for example, you cannot put another electron into the same state, okay. So, this is the Dirac sea, and Dirac sea is completely filled up. Now, this led to some interesting physics essentially, okay. So, this led to some interesting physics. Now, what happens is that what happens is that imagine that there is a photon, okay. This I cursorily mentioned in the last class because we did not have enough time essentially. So, cursorily mentioned that that suppose if there is a photon of enough energy which is greater than twice the mass of the electron, rest mass of the electron. So, what does it do? Okay. So, this photon, suppose if it hits, okay. So, this hits the negative energy state sitting here essentially, negative energy state sitting here. So, what happens is a photon hits a positron, I call it as E plus. I will tell you why it should be always be positive charge, because I will let you know essentially in a second, okay. And this, or this has negative energy is negative, this gives me an electron of positive energy. So, this gives me an electron like I depicted in the picture. The photon comes, hits an electron out of a now, and it gives you electron of positive energy essentially. Now, you have to be remember that the photon, minimum energy of the photon should be at least twice the mass of the electron mass, because this has a negative energy which has minus mc square, and the photon the electron which comes out should have a energy, at least minimum energy, rest mass energy of plus mc square. So if you want to have a photon which should kick out which should kick out a negative energy electron from the Dirac sea, it should have at least twice the mass of the electron essentially, because it has to jump from the negative barrier here, this is minus 2 e m c square, and then come to first state here essentially. So there should be, okay, you realize this is minus mc square minus mc square, that is plus mc 2 mc square plus 2 mc square essentially, minus mc square minus mc square, so that gives you plus 2 mc square essentially. So this should be the photon energy, minimum photon energy, so that it kicks out. Now what happens to the vacated spot here? The vacated spot here is called a the vacated spot here is called a hole. Now what is the charge of the hole? What is the charge of the hole? Now the total charge what we see is Q is equal to Q vacuum, the vacuum total charge, minus electron charge essentially, because essentially we have released one electron, okay. So that becomes the observable charge minus electron charge, so that becomes Q vacuum minus of mod E. Okay. So that becomes Q vacuum plus mod E. So the total charge, now imagine that these are all negative energy charge. Now if there is a hole, now what we are seeing, okay, the total charge of the Dirac sea, the total charge is Q. Now the total charge has one electron missing essentially, so one electron missing. So this is the vacuum, okay, of the one electron missing, but this is the electron of negative charge, okay, if the electron of negative charge, but it will appear of negative energy, sorry, electron of negative energy, the observable charge, okay, the observable charge Q observable is equal to Q minus Q vacuum, that is equal to positive electron charge essentially. Now this is equivalent to observing a positive charge, because all of them are negative energy states essentially, negative energy states, they are all completely filled. The total Dirac vacuum has some charge Q, say for example, have some charge Q, but they are all filled up, okay, it is a lowest energy state essentially, they are all filled up essentially. Now if you remove one particular charge, okay, one particular charge from there essentially, now this will appear as a positive energy particle, okay, this will appear and this will appear, this is equivalent to, adding a positive energy start, okay, this is equivalent to adding a positive energy particle, because the total charge of the Dirac C is always conserved, the total charge of the Dirac C should always be conserved. So, if you remove one electron from there, okay, because you are always measuring everything, this is equivalent to adding a positive charge, this is equivalent to adding a positive charge, which is nothing but the whole essentially. This is equivalent to adding a positive charge, because you are removing a negative energy state, you are removing a negative energy charge, which is minus of minus mod E. This is equivalent to this is electron essentially. Removing from a negative energy state, which is already a field state. So, the total charge of the vacuum, which should be sort of a constant essentially total charge. So, should be, if you remove one, should be equivalent to observable charge, should be equivalent to a positive energy particle essentially, adding a positive energy start essentially, because we are assuming the total charge of the vacuum is infinity essentially, it should be same essentially, it should be remaining of the same essentially. Okay. Then so now this hole which has come out will have a positive energy, Now at some point people thought historically, let me just give one historical comment saying that people thought this positive energy hole could be proton, this could be proton, but then it was ruled out by Oppenheimer, showing that the energy, the mass of the electron which is being kicked out should have the same mass and the same spin as the electron essentially. These states should have the same mass and same spin, it has been shown. So, these are exactly something called essentially, these are exactly the same things as the electrons, but with a positive charge essentially, and they have the same mass. Now, this also led to so this should be a positive charged particle, this is a positron, and now we can show that this is possible, such a process in which E minus, where E is positive, plus E plus E is also positive, will lead to 2 gamma, 2 photons. So, this is the thing called electron positron pair annihilation. Okay. So, the electron positron annihilate to give you 2 photons. We will write a relativistic process for corresponding to it in a few minutes. So, what is happening is that now this positive energy state is actually, though it is a hole, it has a positive energy, and I will write down its it is a physical particle, because you can actually observe its mass, you can actually observe its charge, and its properties can be determined to be exactly the same as the electron essentially. We can show them explicitly. Okay. So, the electron state, let me write down for a more historical feature, you can look at Sakurai's excellent advanced quantum mechanics book. So, charge, energy, let me write down this table and then momentum, spin, helicity, relativistic velocity. When I say velocity, it means relativistic velocity. So, electrons minus E negative energy. Electron with negative energy has negative energy P H. I will introduce this operator in a second, essentially in the next lecture. Sigma dot P bar, helicity, all these operators will be introduced in the next lecture. C, and positron state has E positive, positive energy P, the same spin, sigma dot same helicity, and the velocity is the same. So, there is an interpretation here which goes into, which comes into a bit later in field theory. Essentially the interpretation is that the positron wave function, the u wave function, the whole is nothing but a electron which is moving backward in time, essentially moving backward in time essentially. So anyway, I will continue with this discussion in the next lecture. Okay, I will stop here right now. Essentially in the next lecture I will continue the discussion, and then we will see more details about this essentially. So let me stop here. Thank you very much.